Alrighty, so we are back and we are going to be going over logistic regression. This is a really nice algorithm. I think you're going to enjoy it. So up till now, we've done linear regression, which is where we're making a prediction on some value. In our case, that what we did way back was the house cost based on square footage and other features. So linear regression, multivariate, and single variable is all about making that prediction. So you fit the line that fits the data the best so that you're able to make that prediction. Logistic regression is a completely different animal. In logistic regression, what you're trying to do is you're trying to find a function that will allow you to sort data into, for what we're going to be doing, one of two categories. So it's a binary classification. And so examples of that are things like, is an email spam or not spam? Or is a tumor cancerous or non-cancerous? Things like that, because it turns out binary classification is extremely useful in the real world because a lot of the times it's either one thing or the other. So logistic regression is actually very useful. So that's what we're going today. And let's go to the next slide and see what we have. So in logistic regression, we're going to kind of think of the two groups as a zero group, which is going to be negative. So 0 is going to be the negative class. And when we say negative, we don't mean like it's a bad thing. It means the absence of something. So negative is the absence of some trait that we're sorting by. And then the other group is going to be the one group. That's supposed to be a one, I promise. And so this is your positive class. And it's positive because it indicates the presence of something. So presence. Alrighty. So in our case of talking about the email, if we're checking to see if the email is spam, if it is a 0, it would be not spam. And if it would be a 1, it would be spam. So the absence of spam is the 0 group. The presence of spam is the 1 group. Same thing for the tumor. If we are looking at that, if we're looking to see if a tumor is cancerous, 0 means that it's not cancerous. And then call it cancer. Well, that's hard to spell. And then the 1 group would indicate the presence of cancer, so that would be cancerous. Okay, so your 0 group is the absence of whatever trait you're kind of sorting by. The 1 group is the presence of it. It means it's there. Alrighty, so not too bad. Let me clear this. Now we've talked about that. And we will go to the next slide and start actually looking at how we sort this stuff. So here we go. Now, if you kind of think about it, the linear regression that we've been doing is fitting the best line possible to data, right? So if I had data that looked maybe something like, let's see, I'm going to call the x-axis tumor size, where that direction is getting larger. And then up here, I'm going to put a 1 group and a 0 group. The 1 group is, yes, cancer is there. The 0 group is no, cancer is not there. Okay? So as the tumor size increases, this is what we might get. So when the tumor size is very small, we might have a whole bunch of data in the 0 group for the no. And then when the tumor size gets to be larger, we might wind up with a lot of the values in the yes grouping. Alrighty. Now, if I fit a line to this data like that, we'll just say that's the way that the line would fit. It does a pretty good job of separating the two groupings. This is just linear regression. If I had these data points, these training examples right here, and I fit a line, it seems to do a pretty good job separating them. But there are two reasons why we don't want to use the linear regression to sort things into groups. It's a pretty bad idea. The big one, the absolute big one, is what happens to a linear fit when you have an outlier. So I'm going to now not change, I'm going to add a data point right here. Now, if I fit the line, what does it look like? Well, now this line, which was here, is going to shift somewhere like that. It's going to do a very large shift due to having that outlier. And the further the outlier is located, the more it will shift our line that is the best fit. We don't want to have our line be that sensitive. We want it to be insensitive to outliers. We want them to handle outliers just fine. Outliers should be the bread and butter. They're the ones that are so large of a difference, it's obvious what group that they should go to. So linear regression won't handle that whatsoever. And that's the practical reason. The other reason is that when we were doing our predicted Y value for the houses, we saw that the output could be very large. It was, in the hundreds. And what I want to do is sort things into either a 1 or a 0. So I don't want to wind up having to sort things with some arbitrary value in the mid hundreds that if it's above that, it falls in one category. If it's below it, it falls in the other. So those are two reasons why we don't want to use linear regression to sort data. We want to use logistic regression. And so what we want, if we had our perfect example, we want to be able to take our training examples, do some sort of transformation on our data, and then have it map into either a 1 or a 0. So our best case is to map our output directly into a 0 group or a 1 group. Okay, so it would be really nice if we had a function that could take any kind of input and it would give us some value between 0 and 1. Preferably really close to 0 when it's supposed to be 0 and really close to 1 when it's supposed to be 1. Alrighty, turns out that function has a wonderful name. Let me go to that. Next slide, you ready? Excited? Dun, da, da. Sigmoid function is what we're going to use. Huzzah! Love the sigmoid function. So what is the sigmoid function? Well, the sigmoid function is one of those functions that once you use it, you'll wonder how in the world you are able to do things without it. It's just extremely useful. What it does is, well, let me define it first. It's 1 over 1 plus e to the negative z, we'll say. Okay? And we can say that it is the z can be given to us by our hypothesis function, our theta transpose x could be what gives us our z, but don't worry about that right now. The main thing is, what does this sigmoid function look like? Alrighty, so to get that, I'm going to erase what I have up there at the top. So I'm going to make my eraser super big and take all this out. Alrighty, so what it looks like is this. Okay, we'll put a 1 here. And we'll put a horizontal asymptote there for absolutely no reason. Alrighty, and if that's 1, this is 0.5. This little mark right here. All right, so what does sigmoid function look like? Well, it looks like this. It's actually a little bit steeper. I need to come in a little more asymptotically, but the top part is more accurate than the bottom one, but you get the idea. So let's run some examples. So if my z value is, let's say, I don't know, 9,000, okay? What I would like for it to do is to map that as a 1. And let's see if it does that. So if z is 9,000, if it's super positive, we're going to say this is kind of like the tumor size. If I have an extremely positive value, it needs to go to group 1. Okay, so I want it to map to group 1. So when I put the 9,000 in here, I'm going to get 1 over 1 plus e to the negative 9,000. Well, e to the negative 9,000 is basically a 0 because it's e 1 over e to the positive 9,000, which is a giant number, and 1 divided by that is almost 0. So this term goes to 0, and what do you have? You've got a 1. So when I pop in a 9,000 for my z value into the sigmoid function, I wind up mapping into something that's really close to 1. Alrighty? Now what if I do a z of negative 9,000, something that's really, really negative? The tumor size doesn't really have an analogy. You can't go into a negative tumor size, but you get the idea. If it's something that's should be in group 0, it has a negative value. It's super, super unlikely that it would be in anything other than group 0. What does that look like? Well, when I plot that out, when I plug that in, I get 1 over 1 plus e to the negative 9,000. Alrighty? Well, that's going to become e to the positive 9,000. The 1 isn't going to matter. This whole piece down at the bottom is going to be heading towards a very large value. 1 divided by infinity is approximately 0. So it sorts it into the 0 group. Alrighty? I hope you like that. That's just really, really cool. It's one of my favorite things. So this sigmoid function is going to be the workhorse for the logistic regression. We're going to be taking our hypothesis function, the theta transpose x, just like we have been. We're going to, that will be as a z, we're going to call it just z. We're going to put that into this exponential here, and as a result, the sigmoid function, it will, if it's a really positive value, it's going to map to a 1. If it's a negative value, it's going to map to a 0. Alrighty? And so, just as an aside, the sigmoid function is actually related to the normal distribution, the bell curve. And this is just a nice little aside. Let me clear some of this. Alrighty, get rid of some of this. So how on earth is this related to the normal distribution? Well, it's kind of a hand-wavy way of thinking about it, but I take great satisfaction in this. So let's say that we are going to be accumulating area under the sigmoid curve, okay? And so if, how to say this? I start off, can I say that? Total amount. You know, I've taught this way 2 or 3 times, so I want to. Let's just we'll go with it and we'll just have fun. Um, so when you're, I'm trying to say this without saying it. Let me give you a real world example. Let's do it that way. This might make more sense. The sigmoid it occurs naturally when you have something that is accumulating um, an amount of um, data. I don't even know how to say that. Let me give you this example. I have a spot of light. Okay, this is a bright spot of light on some surface. And now I'm going to take a, we'll say a nice card, and this should be wider. Let me make it wide. Okay, I'm going to start sliding the card in front of the spot size, this spot right here. What does the distribution for the light look like when I start to accumulate the amount of light as I shift the card in front of it? Well, it starts off accumulating very little right here. And then it starts to accumulate more and more and more and more as it as it goes in front of the light spot. And then, boom, right over here. You, at this point, are accumulating very little light. It's a diminishing return. If you graph out the amount of light as a function of the position of the card as it passes in front of the spot, it's a sigmoid function. It just kind of falls out of that. And if you think of similarly, the total probability underneath a normal curve, what does it look like? Well, we've got the normal curve. Looks like this, right? If I'm accumulating the total probability for the normal curve, as I'm moving a card across in this direction, what happens? It starts off with very little, then it increases, and then it starts to tail off and decrease. That's what is happening with the area under the sigmoid curve. It has this relationship to the normal distribution, the normal curve, I should say. Um, and this is what it looks like in the real world. Anytime where you have something that starts off slowly, kind of expands rapidly, and then it tails down, um, you can always model it with a sigmoid, which is really nice. And now you have something other than a normal curve that you can actually start thinking about these things with, which is really, really cool. That's an actual experiment that you do in the laser lab. I got to do that one when I had no idea what I was doing and was scared enough I was going to put my eye out with the laser. I still did it anyway. So that's the sigmoid function, and that's why it's incredibly useful. The sigmoid function takes any value and maps it to something that's either really close to 0 to really close to 1, and every value that's in between. And what I was saying is that this is a little bit sharper than this. So there's not a lot of time that it spends in this interior. The values don't tend to settle at 0.5. You either get something that maps pretty close to 1 or pretty close to 0, typically. It can fall right in the middle, but that's not typical. Alrighty, so now that I've beaten that horse into the ground completely, let's go to the next slide. Alright, so when we're talking about this, and we have this 0.5 as kind of like the center point, right? So this this is kind of the point at which it transitions to either group 1 or group 0. So if our sigmoid function maps out a value that is greater than 0.5, we want it to map to group 1. It's more likely to be in group 1 than in group 0. If it is less than 0.5, we want it to map to group 0. So that's this 0.5 is going to be kind of our boundary that we're going to set. Anything above it, when we do our sigmoid output, we want to map to group 1. Anything below it, we want to map to group 0. That's all we're going to do. All right, piece of cake, no worries. Woo! All right, so let me go to the next slide and talk about what we have going on here. If I can get the PowerPoint to move. There we go. All right, let me clear this. We don't need any of this anymore. Yeah, I don't think we do. We can go without it. So, what is the actual function doing with the theta transpose x? Okay, so in linear regression, the theta transpose x was used to find the set of values. Remember, it's just, we have theta transpose x is theta 0 x0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 ... right? So this is setting a line in linear regression that fits the data the best, because we had our whole cost function, which is looking to see how close our line was to most of the data points. So that's what's going on in linear regression. But what's happening in logistic regression is something completely different. So in logistic regression, we are going to have two sets of data. Hopefully the data is really nice. Like, no, you're never going to have data that looks like this, ever. But we'll hope. In the best world, we'll have something that looks like that. What the theta transpose x is going to be doing in logistic regression is not trying to fit a line that fits the data the best. We want to fit a line that divides the data the best into the two groups. So we want a line that will separate the two groups. This line is called the decision boundary. Alrighty? So our whole purpose in this theta transpose that's trying to get all of our weights, our theta 0, theta 1, theta 2, theta 3. Our whole goal is to find a line that will divide the data into the two groups. And the data can be extremely messy. I'm going to make an example here. Oh boy, that's a lot of x's. And then maybe some zeros for group 0 maybe. I don't know. All right, maybe the data looks like this. That would be really weird data, but let's say it did. Your decision boundary that it's going to try to find the thetas that will generate a line that divides the data into the two appropriate groups may look something like this. Okay. We are no longer doing a linear regression. We are going to be working with generating decision boundaries that are whatever shape is needed to best divide the data into two groups. So we're no longer going to have nice straight lines or even three-dimensional straight lines or anything like that. We're going to have curves and very strange shapes. And the way that we generate those shapes, those curves, is by finding the thetas that will yield this line that divides the data the best into the two groupings. Whew. I know that's a mouthful. All right, I'm going to pause here for just a second, get some water, and then we will pick right back up. Okay, so we are back, and I'm going to clear this screen and go to the next slide. So, alrighty. Now, we have kind of a new way to interpret our hypothesis function, in that our hypothesis function now is going to be used to find the decision boundary. And so to go with that, we also need a new cost function. Okay, our old cost function, it looks like for the linear regression, j is equal to 1 over 2m summation I from 1 to m bracket. We had the h of x, I. Try that again. H of x, I, and then minus y, I, and then that was squared. Okay, so this gave us our y hat, and that was the actual data value. This is just our MSE that we were working with, right? And it did a great job for being able to find the line of best fit. But now, that's not what it's going to be doing. We don't want it to try to fit the data the best. What we want is for it, whatever the hypothesis function is, when it maps into the sigmoid, we want it to output a 1 or a 0 depending on which group the data point belongs in. And so what we're going to do is, if we look at the old cost function, not only is it not going to do that, I should also mention that it is going to result in something that's non-convex. So it is not a bowl anymore. It is something with several local minima, and you don't know which one you're going to settle into. Okay, so we need something that's completely different from this for our new cost function for the logistic regression. So I think we can do it. It's going to take a little bit of math. But here we go. We're going to start it, and then we're going to finish the math next lecture because, wow, is it complicated. Alrighty, but it's fun. So we need a new cost function. And what does the cost function do? Alrighty, well, go to the next slide before I get too far into this. Well, the cost function's goal is to see how well our guess fits the purpose of whatever we're trying to do. In the case of linear regression, we're trying to fit the line that is closest to the data. In the case of logistic regression, we want the cost function to have a very low cost if it sorts something that is in group 1 into the 1 group, or something that should belongs in group 0 in the group 0 group. Can I say group again? Maybe. So the cost is going to have a completely different purpose in the logistic regression. In logistic regression, the cost function is that the cost function's function. The cost function's goal is to correctly sort each of the data values, each of your training examples, into either group 0 if it's supposed to be in there, or group 1 if it's supposed to be in that one. Okay, So the new cost function is going to look way, way different. So here we go. So the new cost function, you're going to love this. Alrighty. It's also going to be j of theta. Those are the parameters that we're trying to set. But this is now going to be a piecewise function. Alrighty. So j of theta is equal to, here we go, negative log of h of x if y is 1, and negative log of 1 minus h of x if y is 0. Now, these look like they fell out of the sky. They did not fall out of the sky. Alrighty. What do these things look like if we graph them? Well, if we graph the first one, we get something that looks like this. Okay? Now, we're going to say that our cost is over here, and this is some x value. Alrighty? This is when y equals 1. We're going to use the negative log of h of x. What is it saying? Well, if the vertical axis is the cost associated with sorting into group 1 or group 0, because that's what our function is going to do. It's going to take every training example and either put it in group 1 or group 0. If it belongs in group 1, let's say it's somewhere out here, right there. Maybe this is, our h of x that has been sent into our sigmoid function. So this is 1 over 1. And is it plus or minus? I always forget, is it plus or minus? Plus e to the negative z, where z is theta transpose x, which is what our h of x is. Alrighty. So if it outputs a value that is 1, or that is something positive, something greater than 0.5, the cost, which is the y value of this function, is very, very low. It is something that is, this difference right here. I'll even change color and try to color that in. It's this difference right here, right? That is really close to a 0 cost. So if it belongs in group 1 and the value is out here, it will have a very low cost. It correctly sorted it into the correct group. Okay. If, however, it says that we're going to go with our h of x is something that's in the negative direction, that will map to our a value close to 0 somewhere over here. It's supposed to be in group 1, but when you run the actual algorithm, it says it's supposed to be in group 0. That means that it's going to have a very high cost. Okay, so now let's go with that. My dog is barking in the background. Go doggy. Gonna drive me crazy. Now let's look at this one. Alrighty, this one looks like this. Alrighty, and so this is when y equals 0. Alrighty, and so let's say that my sigmoid output is somewhere in here. All right. if it says that it should be sorted in group 0, and it's supposed to be in group 0, this cost is going to be very small because it's very close to 0 over close to 0. If it guesses incorrectly, once it runs it through the sigmoid and says that the value should be sorted into group 1 when it's actually group 0, then the cost is going to be very high. So what we're doing with these two functions up here is if the algorithm sorts a data point, a training example, into group 1, if it says it is 1, it's close to 1. When you evaluate it, it is close to a 1 when the sigmoid gets done with it. And it compares that to the actual group it's supposed to be in. We'll say y equals 1. Then the cost is really small. But if it sorts it into the wrong group, it has a huge cost penalty that is going to get thrown in on it. It's going to jump the cost up dramatically. Same thing for if you have an item that should be sorted into group 0. When you run through the sigmoid function and you output something that's near 0, you have a very small cost. It did it correctly. When it compares it with the actual y value, it will say, okay, that was a very low cost. It sorted into the correct group, and so it's good to go. However, if it says that the value is somewhere over here and that it belongs in group 1 when it should actually be group 0, again, it penalizes the cost function drastically. So what we have with these two functions up here is we have an extremely aggressive way of forcing our algorithm to find a decision boundary that the vast majority of the time, should be sorting things into the correct category. It is going to do its absolute best to try to avoid these large cost penalties for when it misclassifies things. And the way that it's going to do that is it's going to make changes to our theta parameters, just like it was doing before, so that it finds the decision boundary that fits the data the best. We're going to pick up here with the next one, but I want to say one last thing. This expression right here is where we're going to start with. This piecewise function has a very special name. This is the log. How do you spell likelihood? Likelihood function. This one's famous. If you've done some of the advanced statistics and some of the other data analysis courses, you've seen the log likelihood function before. What we're going to do with the next lecture, though, is something I hope you have never seen before. We are going to take this function here. We're going to figure out a very clever way of taking the two pieces and putting them into a single expression. And then we're going to take that expression and go through the partial derivative, which is absolutely astonishing how bad the math gets on that until you do some work. We're going to do some amazing work with the next one. So I hope you enjoyed this. Our goal now is sorting things into the correct group. Y'all have a good day, and I will see you next time. Bye, everyone.